Welcome to 3.5. We're talking about exponential and logarithmic models. Lots of real-world examples of these. And there's actually some notes on some different looking graphs. However, I would suggest this one looks like perhaps that's logarithmic graph where we have an asymptote right through here. This one might be logarithmic. This looks like exponential growth. This looks like exponential decay. This one, this bell curve, there's another name for that, but bell curve serves our purposes very well. We haven't really studied graphs, functions that give us that, but we've studied functions that give us logarithmic graphs and exponentials. And we haven't studied graphs that look like this or functions that give us graphs like this. And real world, I think that you may be well aware of some real world examples that go with bell curves. You know, we're plotting, that doesn't work for this particular curve, but a bell curve shifted over this way. We're plotting how tall the students at our high school are. And we would expect, you know, by the time we get into, let's say how tall females are at our high school. And by the time we get to like 5'6" or so, we're going to be near the top of that bell curve, I believe. But by the time we get to 6'1", there may only be one or two, you know, girls from the basketball team, volleyball team, or, you know, don't have to put them in a sport. And by the time we get approaching 0, we won't have anybody at a height of 0. So we get this bell curve. You would oftentimes associate that with test scores. And this graph is like a population model. Like if I introduced a pair of rabbits to a forest preserve that for whatever reason had no rabbits, or we could say a pair of guppies into a 100-gallon fish tank that had no fish in it. The population we would expect to start increasing and then increasing more and more rapidly, but there's a carrying capacity. There can only be so many guppies. Likewise, you'd think, well, you're going to have billions of rabbits, but at some point more and more rabbits bring in more and more prey, and there's still only so much supply there for the rabbits, so there's just a capacity. So these are nice real world curves. Logarithmic graphs are real world, exponential real world. So here we go. The book talks about those, and they show you what the functions look like that produce these types of graphs. Now we ought to know already logarithmic, so maybe it's this one, maybe it's this one, exponential, but these ones we don't know. So ideally, we recognize this as an exponential function, but it's negative, so it's decay. So ideally, we just look over here and say, well, the only one that looks like exponential decay is E. However, what I really want to do, the reason I'm not showing you the notes on this is so you can handle, hey, oh, I haven't seen that function before. I want to know what the graph looks like. Graphing calculator is not convenient. So what I would do is I would look for MyVox. In this case, what makes the exponent 0 is 0. And e to the 0, put in 0 for x and I get 0 up here. E to the 0th is 1. 0, 6 is a point on the graph. 0, 6, nope. 0, 6, close, but nope. 0, 6, nope. 0, 6, nope. 0, 6, yep. 0, 6, nope. So I think this one's E. I think that's E. Now, if that's not enough, and let's say this one looks like it's going through 6, then the next thing I might do is say, what about big X? If I put a big X in here, I get e to a big negative. That's 1 on e to a big positive. That's 1 divided by a massive positive. It wants to get close to 0. It wants to approach 0 as we put in big X, and sure enough, this one is approaching 0. What about big negative X? Big negative X gives me e to a big positive, and e to a big positive gets big, and this makes it 6 times as big. As we go to the left, this graph is going up. It's closing in on 0, so this graph is going up. I'm not trying to imply that that's an asymptote. It's just going to go up boundless this direction. And that was maybe not important for us on 8, but it's going to be important on 10. Now this is very faint, but this is a 2 right here. That's a squared in there. So I don't know what it looks like. So I'm going to go MyVox. What makes the exponent 0 is 2. If I put in 2, I get 2 minus 2, 0 squared, 0, negative 0, 0, 0 divided by 5, 0, e to the 0th, 1, 1 times 3, 3. So I'm looking for a graph with a point at 2, 3, and not just a point at 2, 3, a graph with a point at 2, 3 that might look interesting. 2, 3. That's a pretty interesting point on that graph. 2, 3, nope. 2, 3, actually, 2, 3 might be in play on that graph. 2, 3, don't think so. 2, oh, wow, that's pretty close. Wait, we're counting by 2s. I guess we're counting by 3s here. It's maybe in play here. So let's go a little bit further. Let's go big X. If I put in a big X value here, I get big positive minus 2, still a big positive, squared huge positive, negative, the opposite of a huge positive is the opposite of a huge negative on 5, which is a huge negative. E to a huge negative is 1 on e to a big positive. And 1 on e to a big positive wants to be 0. This thing wants to approach 0 to the right. Big negative. Put in a big negative here. This went back in and filled in that this was approaching infinity to the left. Put in a big negative here, and I get negative minus 2, big negative squared, big positive. Opposite of big positive, big negative. Oh, so it's big negative on 5 again. E to a big negative is 1 on e to a big positive. It's 1 on e to a big positive. It's trying to be 0 again. So we approach 0 in both directions, and we have an interesting point at 2, 3. I'm pretty convinced this is A. All right, my box, 0. Put in 0, I get 4 on 1 plus e to the 0. E to the 0 is 1. So that's 4 on 1 plus 1, 4 on 2, 2. Look at 0, 2, and maybe it's an interesting point. 0, 2, nope. 0, 2, nope. 0, 2, yep. 0, 2, nope. 0, 2, nope. 0, 2, yep. I'm leaning toward F because it does look kind of like an interesting point right there. Big X gives me e to a big negative right here, which wants to be 0. Oh, 4 divided by about 1, a little bit more than 1, wants to be 4. It's getting sucked into 4 here, it looks like. Big negative X. E to a big positive becomes huge. 4 over 1 plus huge is 4 over huge. It wants to be 0 as we go to the left. So there we have it. So all of that information, if I was graphing it, gave me a point right here, told me eventually I want to get to 4, eventually to the left I want to get to 0. Well, sure enough, there's my population curve. Okay, complete the table for a savings account in which interest is compounded continuously. Now, earlier in this chapter, in the notes section, you had a formula for this. The amount we end up with equals principal, what we started with, times e to the RT. And that is a convertible formula, as you'll see, where in this case we're talking money. Amount we end up with equals the principal, the rate times the time. But you'll see this maybe be like y equals a e to the xt or something like that. So anyway, let's take a look, or actually maybe xr instead. So we have initial investment of $2,000, and the annual rate, the annual percent is 2, and I'm going to jump to this one. How much will we have after 10 years? So I don't know how much I end up with. I do know that I started with $2,000. That's e to the, watch this, per cent. Miles per hour. If I went 100 miles in 2 hours, that's 50 miles per hour. It's division. Per is division. Miles per hour, divide miles by hours. Percent, divide by cents. Per division, cents, 100. Divide by 100. 2 divided by 100, 0.02. And I know that you've learned just move the decimal 2 places, but to turn into a percent, we need to divide by 100. And then it says after 10 years is how long we're letting it run for that problem. So, oh wow, that's really just straightforward. That's just calculator entry. Clear out my calculator here. So we get 2,000. Second e to that's second ln. 0.02 times 0.02, that's a times 10. And I've got $2,442.81. Of course we want to round to the nearest penny here. All right, time to double. Now take a look at this. You're going to see that this becomes pretty easy for us. Time to double. Well, if I start with 2,000, that means I need to end with 4,000. Equals 2,000. E to the percentage is still 0.02, but I don't know t now. So this is my troublemaker here. I want to divide by 2,000 to get this alone. E to the 0.02t equals 4,000 divided by 2,000 equals 2. Okay. Now, I'm going to put a 1 here just for emphasis. If I divide it this way, I put a 1 here. This could actually just be 1 and this be 2. And let me put that into context. You invest $2,000. You want to know how long it takes to get to be 4,000. I invest $1. I want to know how long it takes to be 2. So we don't even need a money amount given in order to figure out how long it takes to double. You can just invest $1, turn it into 2. So now I need to solve for t, and that's what the earlier section, I think it was 3.3, talked about in this section, was how do we solve for an exponential variable? We use logarithms, in this case base e. So I'm going to go ln e to the 0.02t equals ln 2, but ln, of course, because we're base e, but 0.02t can come out in front. The exponent that turns e into e is 1 equals ln 2, and t equals ln 2 divided by 0.02. And it's worth pausing just for a second and giving that some thought. What if this said, how long does it take to triple? Well, this would be 6,000. This would be 6,000 divided by, this would be 3. This would be 3. This would be 3. This would be 3. Oh, it takes that long for money to triple at 2%. Times how long would it take for your money to be 10 times as big? ln 10 on 0.02. So let's go ahead and grab that one. On ln 2 divided by 0.02. And we've got, takes quite a while, 34.657 years. A little bigger challenge if they want it in days and months, but we can do it. Okay, so now they tell us how long it takes to double. We started with 1,000. It doubled to 10,000 in 12 years. 1,000 e to the r, oh, I don't know r, times t, 12. But notice, time to double problem, I didn't need 1,000. I could have just started with 1. And gotten to 2. So now I just need to solve for r. So I need an exponent. What exponent? What logarithm do I use? ln, because our base is e. So ln 2 equals 12r. R equals ln divided by 12. ln 2, excuse me, divided by 12. So ln 2 divided by 12, and I'm going to record this as 0.0. Nope, don't make the mistake you talked about earlier. I'm going to record it as 5.776%. And I'm going to understand that's rounded. That's a rounded value. And now what I'm going to do for the next problem, I'm going to come back and talk about the danger in that being rounded. Yeah, that's right. You're going to see the danger in rounding this thing as we move into this next problem. Now I want to know 10 years. Okay, so what am I going to end up with if I start with 1,000 e to the rate right here? My rate, if I put in 5.776, that's rounded really nicely. However, I'm going to multiply that by 10. I'm going to use it as an exponent, then multiply. So when I round it to 5.776, it's an error. When I multiply that by 10, it's a bigger error. When I use that as an exponent on e, probably a bigger error, times 1,000. I just keep magnifying my error here. And our calculator gives a solution to this. I'm going to use my answer that's in my calculator, this value right here, ANS, times 10. And you could do this. You could go 1,000 second e to that, and you could type in 0.057762265, and you'd be in pretty good shape. However, this ANS button, at this stage I suspect many of you know this, and I suspect some maybe have never used it. This ANS button will bring the last answer forward. So I'm going to go second ANS, and that's a really good habit to get into on these problems, because clearly we need to be correct. We don't want to use magnified errors in our solutions here. And this is asking for an amount. We need to be correct to the nearest penny. So answer times 10. And we end up with $1,781.80. And it's very possible, if we use this rounded solution for our rate, that we wouldn't get the exact same solution. Happens a lot. On your next test, you're probably going to have some 10-point word problems like this, and if you're off by a penny, there's going to be a rounding error. If you're off by like 6 cents, then you might have a severe rounding error on it. Okay, let's continue here. Amount after 10 years. Here's my start amount. So I end up with $385.21. I start with 300. E to the R, I don't know R, but I do know the time after 10. I do know the time is 10. So I get E to the 10R equals 385.21 on 300. And I get a lot of people that feel compelled to divide that, and I like to just go to my calculator once. If I take the natural log of both sides, ln of this becomes just 10R equals ln of star. I think I've talked about star before. I'm just using star as a placeholder for this value. So R equals ln star, not star divided by 10, but ln star, all of it, divided by 10. So let's figure out what we've got here. Clear this out. ln 385.21 divided by 300. That's my argument for logarithm. Then I need to divide all of that by 10. And that gives me my rate, which is 0.02500. So as a percent, that would be 2.5000. So 2.5% is rounded to 3 decimal places. And now I want time to double. So you could say invest 300, turn it into 600, or you could say invest $1, e to the, I'm going to use ANS, even though, boy, that's just about 2.5%, right on the money, times t. I'm going to have $1. See how long that takes us to get to be $2. ln both sides. ln2 equals ans times t. So t equals ln2 divided by ans. Second negative. If you put 2.5 in there, it could be accurate enough, considering this thing was virtually exactly 2.5%, but not quite. But you might have a little bit of rounding error. So time to double, 27.725 years. Okay, and number 20, let's see, amount after 10 years. I've got my rate, I've got my amount after 10 years. So let's see, how much did I end up with? 2,500. How much did I start with? P e to the 0.035 times 10 years. Oh, well, that's nice. P equals 2,500 on e to the 0.035 times 10. So 2,500 divided by second ln e to the 0.035 times 10. How much did I start with? $1,761.72. Now, that is actually, I would consider that our exact value, because I certainly did not start out with $1,761.720224. So we're going to use that number to come up with time to double. But do I really need to use this to make my amount double? Some people will, but I would say, hey, I want to know when it becomes 2 when it started at 1. E to the 0.035t. ln2 is 0.035t. T was ln2. I have to divide away 0.035. Make sure you don't turn that into ln of 2 divided by this. It's ln of 2, all of it divided by. When in doubt, set it up as a fraction, but I think we can get by without that here. Let's see. ln2, close that parenthesis is what I'm trying to say, divided by 0.035. We got 19.804 years. Okay, so there's a longer page for you. Those are going to take a little bit of time, although I would suggest that you're probably going to be able to work through 7, 9, and 11 quicker than I did. So there we have it. Let me know what I can help with. I suspect maybe we'll have some questions here, but you'll see these model these others very, very closely.